All right, today we're going to dive into something that's a huge deal for anyone working with AI. How do you take these massive, incredibly powerful large language models and make them faster, leaner, and just better? We're talking about supercharging them.
So picture this. You've got this incredible LLM, right? It's brilliant, it can write code, it can draft marketing copy, it can do almost anything you ask. But then you go to actually use it in a real-world application, and you just hit a wall. That lag, that frustrating pause between your question and its answer. Sound familiar?
Well, that lag, that's the problem. For all their smarts, the inference speed of these models, how fast they can actually think and give you a response, has become the new major bottleneck. The sheer amount of compute power and memory they demand is just staggering, and it's slowing everything down and making things super expensive.
So how in the world do we fix this? Well, the answer, or at least a huge part of it, lies in a really clever technique called model quantization. And the idea behind it is actually pretty simple, but so powerful. We're going to trade a tiny bit of numerical precision for a massive boost in performance. And get this, you don't have to go through all the pain of retraining the model from scratch.
Here's an analogy. Think about a super high-resolution photo. It has millions of colors, it looks amazing, but the file size is huge. Quantization is kind of like taking that photo and reducing it to a smaller, more optimized color palette. You lose a little detail that your eye probably wouldn't even notice, but the file becomes way smaller and faster to load. In an LLM, we're doing basically the same thing but with the numbers, the weights and activations that make up the model's brain.
And here's how it works on a technical level. Look at this table. When you go from something like FP16, which is a common 16-bit format, all the way down to INT4, a 4-bit integer, the range of numbers you can even represent just collapses. It's a massive drop, and MAC compression is exactly what makes the model smaller and all the math inside it way faster.
Okay, but wait a second. That brings up a really critical question, right? If we're just squishing all these important numbers into these tiny little boxes, how do we make sure we don't accidentally throw away the vital information the model learned? Because if you just compress everything blindly, your model's accuracy can just fall off a cliff. We need to be smarter about it.
And that is where the really cool stuff comes in. We're talking about advanced calibration techniques. This is the secret sauce. This is what lets us be really aggressive with our quantization, to shrink the model way down while still protecting its intelligence. It's not about shrinking everything, it's about shrinking things smartly.
Okay, let's start with a big one, Activation-Aware Weight Quantization, or AWQ for short. And this quote really nails the core idea. AWQ is built on a very simple and intuitive principle. Not all of the connections or weights in a neural network are created equal. Some are way more important than others. So how does this actually work? Well, AWQ is smart. First, it goes through the model and figures out which weights are the superstars, the salient ones, that have the biggest impact on the final answer. Then it protects them, keeping them at a higher precision. But the less important weights, it quantizes them aggressively. This selective, targeted approach is what lets us get all the way down to 4-bit precision with almost no drop in accuracy. It's pretty brilliant.
Okay, so we've handled the weights, but that's only half the story. There's this other sneaky problem that pops up in these models, especially transformers. You get these things called activation outliers. Basically, a few spots where the numbers suddenly spike and get huge. And these outliers can totally mess up a simple quantization process. And the solution for this is just so clever. It's called smooth quant. See, instead of trying to fight with those massive outliers, smooth quant just smooths out the problem beforehand. It finds those spiky activation values and scales them down. Then, to make sure the math still works out, it balances the equation by scaling the corresponding weights up. The final result is mathematically identical, but now the numbers are much more well-behaved and way easier to quantize.
All right, so we've got these incredible, super smart techniques, AWQ, smooth quant. Amazing, right? But how do you, as a developer, actually use them without getting a PhD in quantization?
Well, that's where the NVIDIA TensorRT Model Optimizer comes into play. You can think of it as the toolbox that puts all of this power right at your fingertips. It packages up all these advanced methods into a library that developers can actually use.
And this thing is absolutely loaded. Of course, it supports those crazy efficient formats like NVP4, and it has AWQ and smooth quant built right in. But the really key thing here, it plays nice with the tools you're probably already using, like PyTorch and Hugging Face.
It even has this awesome auto-quantize feature that looks at your model and figures out the best way to optimize it layer by layer all by itself.
Okay, theory is great. Tools are great. But what about the results? Does this stuff actually deliver when it matters? Let's look at the numbers, because this is where it gets really exciting. The proof is in the performance. Whoa! Just look at these speedups in token throughput. We're talking more than double the speed for Llama Nemo Ultra, 2.5 times faster for Qwen, and a ridiculous 3 times performance boost for DeepSeek R1. That's not a small improvement, that's a game changer.
Okay, but I know what you're thinking. What's the catch? What about accuracy? Well, get this. You get all that speed while keeping over 99.5% of the original accuracy. It's kind of mind-blowing. Up to 3 times the speed with virtually no sacrifice in how smart the model is.
So what does that actually look like? Well, it's simple. You've got the original, slower model and the new quantized one. They both give you the exact same high-quality answer, but the quantized version gets there 3 times faster. Same destination, way faster car. So what's the big takeaway here? It's that faster, leaner, and just way more scalable AI isn't some far-off dream. It's here, right now. For a business, that means lower cost to run your AI. And for your users, it means a faster, better, much less frustrating experience. And the best part? You can start playing with this today. The NVIDIA Toolkit makes it super easy to export your optimized models into a standard Hugging Face checkpoint. From there, you can load them into all the popular inference engines. You can even go to the Hugging Face hub and find models that are already quantized and ready to go. So all of this leaves us with one really important question to think about. With this kind of performance on the table, with almost zero trade-off, is running your model at full precision really a smart choice anymore? Or is it a luxury you just can't afford? It's definitely something to think about. Thanks for tuning in.